So Riemann hypothesized that the critical line where non-trivial zeros can be found is in exactly in which real value is in 0.5. That's the sigma value is equals to 0.5 is where true oscillatory dynamics is found. That the zeta function exhibits the true oscillatory dynamics. What does that mean? It means that for some other sigmas, they don't even, there's no cosine shift. It doesn't even, there's no deep full swing. And at first I was like, it's like what I've observed in other sigmas as I increment the t number, whole number, the starting point is the lowest point. It just keeps going farther and farther. So at first my understanding of that is that for most of the zeta 0 functions in sigma 0.5, I see it, and the starting point is not usually the lowest, that it can go deeper. It can go closer to closer as it increments. So it's a function that isn't flat. It's it shows that it can swing. So it swings. It can get so it gets farther and then closer. So there's a certain oscillatory, a certain resonance, a certain that there's a certain formula, like there's when you pass that function, it you can really see that that it can do a full swing. So it's not flat. It can do a full swing. So it's like as you increase, you can see it maybe going farther, but then it goes back. So it does a circle. It does a full circle, and it passes through 0. So this is the second version. I made some changes. I added 32 more sigmas to test out, and then I curated 40 t whole numbers. So if I see all the outputs by the different sigmas, it's not enough that we test it out to just one t whole number. It has to be tested to several, to different, to a number of range, like a range of t whole numbers. So I have even like a 30 billion, because the database has that 30 billion t, and then non-trivial zeros at the imaginary part is t interval at 30 billion. So I have that. And so, but I am missing a piece, which is the cosine shifting, and I kind of didn't get it until I asked ChatGPT to create me an image of the difference between each sigma behavior, and then that's when I noticed that, okay, so there has to be some shifting of the cosines so that it's passing through. And so for this version, I did not have that tracking the cosine shift. So that way, when I have all the data, I can then see if it is true that that it really is doing so many, like probably about 50-50 shifting, so of the positive negative cosine, that it's crossing over. And that could be the hallmark of the Riemann hypothesis. That's what makes it different from every other sigma. So I'm also using sigma that is very close to 0.5, just to show really the stark difference. That that 0.50 is really very critical. That's really very important. It's the most significant, that even if just a one increment, like 0.01 increment, 0.01 difference, we see that, maybe the either 0.01 from the left or right, that it actually makes so much difference, that we could see maybe less shifting or something, that line 0.5 is really where the non-triviality happens, that we see it doing a full oscillations, that is the function that can output the most perfect oscillations. So that's how I kind of understood it. That's the Riemann hypothesis, that it is only that very special sigma 0.5 that true oscillations occur. So, and that's something I wanted to also see from the data, when I do get that. So I still have to make some changes. I still have to incorporate tracking the positive and the negative shifts, and then we will see if that is correct, that is the only region, that's the only sigma, very specific 0.5, not 0.51, not 0.49, that true oscillation can occur.